Hello everyone, welcome to this SWAM-NPTEL online course on space environment and its effects on orbital spacecrafts. So, in this module we are discussing the effect of plasma environment on the operation of spacecrafts, and in this regard we discussed that spacecraft charging is very significant phenomena which occurs because of the interaction of the spacecraft with the plasma environment. So, in the last session we discussed how to model the spacecraft charging. So, we discussed or we compared, that is the charging, spacecraft charging with that of a capacitor charging, and how it takes the finite time that a spacecraft get charged. And also we just introduced that is called the probe theory. So, you can assume a probe that is also known as the Langmuir probe. So, if you insert a probe in a plasma chamber and you vary the potential of the probe from very negative potential to the positive potential, then you have seen that we have three regions of the current and voltage characteristics. So, one region that is called the ion saturation region, we can use that region to know what is the density of the ion. Then there is the transition region. So, transition region means when the voltage you are increasing from very negative voltage towards the positive voltage, then the electrons get, it can cross that the barrier, the threshold barrier, and then that also goes to the saturation. So, that region when it goes from the threshold voltage to the saturation voltage, that is called the transition region, and that transition region can be used to calculate what is the energy or the temperature of the plasma, and then the density of the electron density you can know from the saturation region. So, these are the things we discussed. Then we discussed how we can assume the spacecraft as a Langmuir probe, because when you are injecting the spacecraft in the orbit, it is in the place, it is in the space environment. But what is the difference between the this spacecraft as a Langmuir probe or a laboratory based Langmuir probe? So, in the laboratory based Langmuir probe, we are applying the voltage and getting the response as current, but here the spacecraft is collecting the current from the plasma and its potential is increasing as if like a capacitor. So, this is the difference between a lab based Langmuir probe and the spacecraft as a Langmuir probe. After that, we derived the Langmuir probe equation and we consider the orbit limited regime. So, if you remember how we defined that is orbit limited regime. So, we assume that the plasma, that is the interaction or the plasma density is low, that there is no individual interaction or that collision between the plasma particles, and their motion is governed by the angular velocity because of the electrical force imparted by the charge body. So, we considered the Langmuir probe as a spherical geometry, then we consider it as a cylindrical geometry as well as the plane geometry. And in this we will continue with this discussion. So, today we are going to discuss again related to spacecraft charging, what is the spacecraft equilibrium potential. And if you remember in the last class we take the case of a bath, and we consider there is a flow of water and there is a outflow, and we say that whenever the water is getting poured, so your level is increasing, means it is building the potential. Now, if you have an outlet, and when the inlet and outlet the flow is it balances each other, then you get a level which is not changing. So, similar thing happens in the spacecraft, we call it spacecraft equilibrium potential. I will discuss that. So, in order to discuss that, we will discuss that that is repelling of like charges, then attraction of opposite charges, and then we will discuss the Boltzmann's repulsion factor. The Boltzmann's repulsion factor here comes from the Maxwell-Boltzmann that velocity distribution that or energy distribution, that also will already we discussed it, but now we will apply all those things. And then finally, we will find out the spacecraft potential, that is the or we will call it a built up potential or the equilibrium potential. So, now just we will start with very simple class 10 example. Suppose you have a charge which is equal to negative charge minus 16 to 10 to the power minus 9 coulomb, that you assume that a spacecraft is having that much charge. So, if that is the charge, then the potential of the on the surface, you just consider a conducting sphere, then you can calculate it by this expression, and the potential will be it is minus 540 volt. So, what does it mean that if the spacecraft acquires negative charge from the plasma, it will acquire the potential. So, you see this potential itself is this quantity is quite a significant quantity, minus 40 volt. So, if the charge increases, that will go even to kilovolt, megavolt, gigavolt. So, that much it can have that much higher potential, but that phenomena is not so simple. Already we explained that in connection with the Langmuir probe, what happens whenever the spacecraft acquires the negative charge. Why it gets the negative charge? Because the electrons they have their lower mass. Lower mass means they will have the higher velocities. So, as compared to the positive ions, the electrons will move faster and they will get accumulated on the spacecraft. So, as soon as it gets accumulated, it will have its own potential energy, and then it will not allow the like charges to come, and then it will attract the opposite charges, means the positive ions it will. So, as a result of this, what happens? So as a result of this, it will have because of first it will acquire the negative charge. So, whenever there is a negative charge, so there is a negative charge. Suppose there is some negative charge, you consider this volume. So, there will be everywhere this environment will be non-neutral, means there will be the electric field there. Okay. Now, this negative charge, what it will, once it is built up its own the potential, the field, it will not allow the negative charge to come, will come under that condition. Even negative charge can come, provided it can overcome this this potential energy or whatever the potential energy imparted by this electric field. Okay. So, what I want to say that, so this whatever this I said, that is the imbalance, because plasma is as a whole plasma is neutral, but here what is happening, plasma is becoming that around the spacecraft is not neutral, it is not, it has become like negatively charged. So, this is the imbalance. Because of this imbalance, there is a plasma sheath, and a plasma sheath, what is the characteristic, the dimension of the plasma sheath, that is the Debye length. So, once the spacecraft is there in the plasma environment, it will be charged because of this phenomena, that already we explained previously also. Now, I am again it is repeating those things. Now, another thing, if you remember, we said that is that spacecraft, whenever it acquires the negative charge, then it is becoming negatively charged, and this environment surrounding the spacecraft is non-neutral. But beyond the sheath, this environment is neutral, though it is charged, the gas is charged, but it is neutral because of the nature or the characteristic of the plasma. Plasma is in general plasma is neutral. So, we consider the plasma potential as phi is equal to 0, and so if you remember, I call the spacecraft as a capacitor. So, one plate is the spacecraft and the other plate is the reference plate. It is the you can consider the boundary of the sheath where the potential is 0. Okay. Now, we will define the what is the floating potential. So, already I said yes. So, I can consider the spacecraft is having a potential relative to the ambient plasma potential, which is defined as 0. So, this is logical, because this plasma outside the sheath there is no net charge. So, there is no net field there. So, I can assume that it is having a 0 potential there. So, this potential, spacecraft potential, it is called a floating potential. Why floating? Because this charge, this potential, it can float up and down depending on what is the dynamic environment. Depending on the environment, the potential will either increase or decrease relative to the constant. What is the sea level here? Sea level is the 0 belt, that is that of the the potential of the ambient plasma. So, pictorially it is shown here like that. So, you see this is the spacecraft, you can just assume this portion is your spacecraft, and then this spacecraft potential, it is from 0 and it is it is going towards the negative, and then it has got some stable potential here. Okay. So, this is, you can consider this as phi, and then again it is going to the plasma, it is going to the 0 potential. So, you can say this, okay, I will write it like phi, it is phi. So, the satellite potential, so you can consider here that is at this point as r is equal to 0. So, there is a sheath, as already I said, in which this phi r varies gradually from the potential this phi to 0. To the ambient plasma where the potential is 0. Now, I can write this mathematical expression like this. How I can write this? Because already if the spacecraft has some charge q, as already I wrote that. So, I can write that potential phi 0, 0 means r is equal to 0 here. So, this will be equal to q divided by 4 pi epsilon 0, then this is the r. So, what is r here? R, I can consider this spacecraft as a sphere. So, this is the radius of the sphere, then the term will come e to the power minus r by lambda d. What is lambda d? Lambda d is the it is the Debye length. Okay. So, now I can write q is equal to, and now here r is equal to 0. So, this term will not come. So, I can write that phi is equal to, so here r is equal to 0, I will not write this term, I will not write this term. So, I can write q is equal to 4 pi epsilon 0 into r, and that is phi 0. Now, at some distance r, the potential will be given by phi at r, at any r, it will be q by 4 pi epsilon 0, then r, capital R plus r, where r I am considering from the surface of the spacecraft. So, that is why I am writing it q by 4 pi epsilon 0 r, and then I will write this expression r by lambda d. Okay. So, if you substitute this q here, you will get this expression. Just if you substitute q 4 pi epsilon 0 r this, so you will get this expression. So, this comes from here. So, what is this expression? This is the expression for the Debye length, and you see the Debye length is actually proportional to. So, I can write this lambda d is equal to, I can take some constant c, then I can write it T e by n e or n p or n 0, whatever it may be. So, you see what is happening here, this Debye length is directly proportional to the its energy or this temperature, whereas it is inversely proportional to the density. So, we will see that whenever we go to orbit like high earth orbit like geostationary or geosynchronous orbit, and when we will calculate the Debye length, very high energy, the plasma species where the density is very low, we will see that it comes in a few meters. So, that whereas where the density is very high and the temperature is low. So, in that case we will say that we will be able to see that the Debye length is in few centimeter. So, then we will still whenever we proceed further, we will discuss what is the significance of this Debye length when I consider the spacecraft charging. Okay. So, this already I told what is capital R, what is small r. So, now the next let us consider the repelling of like charges. So, already I said whenever you are adding the electrons to the surface, it raises its potential, that we already have seen. So, it is the negative. Okay. And this potential, it repels the electrons that try to come in later. Okay. Now, what is that condition? So, condition is that an incoming electron of negative charge q having a kinetic energy E is equal to here just you see I am writing energy E as well as electric field also we write E. So, my electric field E is a vector here, but here since it is energy, it is a scalar. So, that when I write electric field I have to use this vector notation, otherwise it is difficult to differentiate. E, both E are used for energy as well as a symbol for the electric field also. So, what I am telling here, if the the incoming electron, if it wants to get accumulated in spite of that that potential energy q phi. So, in that case this energy, this kinetic energy has to be more than that potential energy, then it will happen, otherwise it will lose its energy. Okay. So, here you see the phi is it is an electron. So, q is negative, and since the spacecraft is negatively charged, so q phi is positive. So, here only those electrons energetic enough, they can overcome this potential and they can come inside this sheath and they can get accumulated on this spacecraft. What will be the condition? The condition is that this E, that is the kinetic energy, it has to be greater than this figure. Okay. So, therefore, the resultant potential depends very much on the energy distribution of the incoming electrons. So, already that is how we represent the energy distribution by. So, we will use the Boltzmann-Maxwell's distribution function here. Okay. So, let us consider the spacecraft is charged to a negative potential phi. So, the incoming ambient electrons they will be repelled by the negative potential. So, if that is the case, then let us assume the ambient electrons, they form the Maxwell distribution, means there the velocity, the distribution, the probability distribution is Maxwellian. So, in that case, so this already we discussed, that is we discussed each term, how we derived this, everything we discussed when we are discussing the basics of the plasma physics, and so this thing already we did it. So, this is the expression for the energy distribution. So, whenever I was explaining this I use this term, I use there half mv square, but here I am writing in terms of the energy. I can write in terms of velocity also. So, velocity means this E I will replace by this terms. So, now because of the repulsion, the distribution of the electrons arriving at the surface are shifted in energy. So, this E will be shifted by the energy q phi. Let us see how it is done. So, now that E, since both are negative, so this will become E plus. What does it mean? That if you plot this Fe, then Fe plus q, it is shifted in left side. So, whenever the cases of the repulsion, so here the energy distribution that will be shifted in the left side because of this term E plus q E into phi, which is a positive term. Now, we will see that this repelled charge spaces, that is electrons, the distributions they shift to the left, just already I told you. Why this is so? Because every particle loses an energy of q and phi, q into phi when they arrive to the surface. Okay. Now, you see this energy cannot be negative, we will see in our next slide. So, what does it mean? That this part which is shifted to the left side, this is the lost, and it represents a lost population. We will see it more here. So, you see this is the expression what I wrote, this is the distribution or the energy distribution of the particles which has come into the influence of this field E. So, this there the energy will be modified by this term. In the neutral medium, it was this term was not there, q phi was not there. So, this is, so this what does it mean? This means the plasma, that is the distribution function of the neutral plasma, but whenever they have reached or they entered to the sheath region. So, this expression is modified by this. Okay. Now, the condition is, you see, this energy is the positive, this is the Maxwell distribution, this is the Maxwell PDF, probability distribution function. Okay. So, if this is the case, so there cannot be any negative energy. Now, in order to know the shifting, what we will do? We will take the logarithm with the both sides. So, we have taken the natural logarithm. So, if I do like that, so it becomes this exponential function. Now, it will become a linear, that it is a linear equation or the equation of a straight line. So, you see this, if I put as y, then E is my variable. So, this I will put as x and this will be the slope, okay, and then this is the constant term. So, if I plot that, the plot it will look like that. Now, whenever if I now substitute instead of f e to f e of phi, then what I will have? I will have something shifted in this direction. So, whatever is going to the negative side, there cannot be that energy cannot be there. So, that part it will be as if it is the lost. So, this I wanted to mean. So, this term is coming, because of this term it will shift towards the left. Yeah. So, this is the term I wanted to tell you, that is that f, this probability distribution function, it has to be 0 when E is less than 0. So, if I use that concept, so it can only shift to the right. Now, we will see the other case. We have seen the repel cases. Now, you see this since the spacecraft is negatively charged. So, it is repelling the electrons, but it will attract the positive species, means the positive ions or the the protons, those things it will attract. Okay. I think this repel species let us complete. Okay. Now, we will write down the current equation, that is the flux or the effluence. So, flux how can I calculate? So, already I told, that is when I am to calculate the flux, I need to use that is the expectation. So, what is, so this is my probability distribution function, this is the random variable and this is I am integrating. So, I am considering here all these the particle is moving in any arbitrary direction. So, it is basically I am writing the expectation. So, expectation of a random variable, it is given by that is the random variable, then the distribution function, and then you have to integrate over that random variable. So, this is I have written in one dimension, but this expression in the 3 dimensional cases. So, now you can calculate the current, and this terms q is equal to minus E, means when I am considering it is an elementary electron and my phi is negative here. Okay. So, this f e is it is a velocity, it is, though I have written is in terms of energy, but you can write it equivalently as a velocity distribution function also. So, under thermal equilibrium you can write this distribution by this function. So, this is possible because this whole term it comes under the exponential. So, you take this part, so it comes under f e is equal to, so as if it is modulated by this term. So, the arriving electron flux, that will be, you can write it like this. So, you just substitute this expression here. So, you can find the arriving electron flux by this expression. So, now you can find the current. So, if you have the cross section, so you will be able to find the current. So, current density multiplied by the cross sectional area. So, this is the expression for the current. So, here what is J 0? So, J 0 I am considering when my phi is 0, phi is 0 means this term is not there. So, I can write my I phi, that is the current at a potential, when the potential is phi, this current is given by this expression from this equations as well as the equations which I have given in the previous slide. This exponential term, this is called the Boltzmann factor, because this thing has come from the Maxwell Boltzmann distribution function. And we have seen that is whatever expression you have derived. So, it is it is valid for spherical, cylindrical, this type of this geometry whenever you consider the probe. So, the next is attraction of opposite charges. So, in our case here the opposite charges will be the positive ions. So, there are this statement is already known, that is that electrons and ions are there in the orbital space plasma, and most of the ions are the O plus that already we discussed, okay, and H plus at the magnetosphere. So, this already we discussed when we were discussing our in the initial days, we discussed all those things. So, what is the thing? The spacecraft is already, it has already got negatively charged because of the impingement of the fast moving lesser mass electrons, and it acquires a finite negative potential. So, now it will, the positive ions are attracted to the spacecraft surface. So, the resulting the resultant potential will be determined by the valence of the electron and the ion currents coming into and going out of the surface. Okay. So, here again we will see that the ions reach the charged spacecraft surface, and in this case the ion gains the energy of q phi. In the previous case it was losing, but here in this case it is gaining this energy q phi. So, now how our this distribution function will look like? Of course, this it has to satisfy this kinetic energy has to be more than the potential energy. So, now you see that the distribution function has been modified like this, it has got modified like this. So, this is the case of the distribution function considering the neutral plasma environment outside the sheath. Okay. So, I will again the way we did it for this the repelled species, what I will take the logarithm, and if I do that, then I can show these two equations like this. So, this term is coming. So, here what does it mean that this will shift towards the in the right side direction. So, this is happening here. So, this is there is no charging, means it is the neutral environment, but on the spacecraft whatever the charges, their energy distribution I can express like that. Here of course, what we have done, we have converted or we have taken the logarithm. So, that is why it has become a the linear function or a straight line. So, what we can show, I will show it in the this coming slides before I finish this. So, so already we wrote these two equations. So, what I told you that is the Maxwellian distribution, they are shifted. In this case, whenever it for the this species like the ions which are getting attracted, for them it is getting shifted towards the positive side. So, this one there you see. So, it has shifted by this much E phi, where E is the charge of the electron and phi is the whatever the already the spacecraft has got the potential. So, if the distribution function Feu measured on the surface of the spacecraft charged to a potential phi s, so I should write here phi s, then the distribution measurement would be shifted from the ambient plasma by an amount E phi s, whatever is shown in this curve. Okay. Now, we will show that even if it is not a Maxwellian distribution, still this shifting will be valid. So, I will end here, and the next class will continue from here, and then we will see that is how to the write a valence, that is the current valence equation using the Kirchhoff's current law, which we described in our previous classes, and we will continue working or discussing this spacecraft charging. Okay, thank you very much.